in picture number one, a long thin rod that, depending on the material, would expand or contract a lot or little if we change its temperature. And you'll recall from earlier in the lesson, we said, oh, well, the change in length is alpha L naught delta T. You guys okay with that? So imagine, as I've already suggested, that I take a metal and I pound it till it's very thin. It's a thin sheet. It looks like a square. It only has 2 dimensions effectively. It's super thin, like aluminum foil, for example. If I were to change its temperature, it would expand in 2 directions. That's what that picture is suggesting on the left-hand side. And interestingly, if I want to get the change in area, of course, it depends on the original area, the change in temperature, and it turns out, if I take alpha, the linear expansion coefficient, and I multiply it by 2, that gives me the area expansion coefficient. Pretty cool, huh? I only have one head nod, so it's like minorly cool. And then 3, if I have a change in volume, it depends on the original volume times the change in temperature, and this thing called beta, which happens to be roughly 3 alpha. Let me make sure we see that. It turns out that if you were working with a solid and you're trying to figure out how much the volume would change, and you only have the linear expansion coefficient, that's all you need. Because take a look. What is 3 times 23? What is 3 times 19? 3 times 3 times that. 3 times that, almost 26, right? 3 times that. So the point is, if you know alpha, you can find the area expansion of something that would only expand in 2 dimensions or shrink in 2 dimensions. You can also find the volume expansion by simply taking alpha and multiplying it by 3 for the volume expansion coefficient. They typically call this guy beta. To be honest, I don't know what the Greek letter is for area expansion, but it's 2 alpha. Isn't that kind of cool?
Is there anything that doesn't expand?
I don't know. Nothing? 0? No expansion.
Zero expansion.
I haven't thought. I honestly do not know, but I bet you could Google it. Is there anything that doesn't expand? All right. Now, something that might be a bit unintuitive, but we need to make sure we're clear as to what really happens here. So you have this sort of conceptual scenario where they've removed one tile from this 9-tile constellation, and they heat it up, okay? When you do that, you might think that these tiles would expand into the hole and the hole would become smaller. That's actually not the case, okay? It's not the case. If you heat up this constellation of tiles, this hole will expand. As these things grow, they'll grow this way and this way, and they'll create a hole that would behave as if there was actually a 9th tile in the middle. Okay? So if you've ever tried to remove a troublesome nut from a bolt, sometimes you'll heat it up in order to get to remove it. And hopefully what you're depending on, assuming they're different metals, is that the nut will expand, the hole in the nut will expand faster than the bolt will expand, and then you can loosen it and take it off. So you often see a lot of gearheads in the garage heating these up to try to get them to be able to remove them from each other, different dissimilar metals. Okay. Very important idea here. So think about the aluminum radiator. Okay? The aluminum radiator is clearly not a solid. It's empty, right? It's a shell of aluminum, and we put radiator fluid in it. But it expands outward when it heats up, as if it were a solid. As if it were a solid piece of aluminum, it expands outward. Thus allowing the fluid inside it to expand, but it still doesn't expand enough, and then I have to have that overflow. So whenever you think about something that's a shell or something with a hole in it, realize that when it's heated up, the voids will expand as if they were solids, or as if they were a full area, such as this one. Okay, so carry that along with you. I think I've said all I want to say. Oh, we've talked about this. This is just three-dimensional expansion, yes? It's not that much more than thinking about. By the way, what would delta V, what's another way to write that?
Well, all the 3, 5 multiplied.
Delta V, say that louder.
It's volume final minus volume.
V final minus V initial. Okay, V final minus V initial. Let me write some math here on the board real quick, just so we're clear. Because you might see sometimes certain types of problems that might be asking you slightly different questions, and I'll show you how to deal with it. For the linear, if I have delta L, is the change in length is dependent on alpha, the original length, and T final minus T, delta T. Well, this is L final minus L initial. Everybody okay with that? I just wrote this out explicitly. If I want the final length, let's say that's my objective. Hey, what's the final length? I can move this over. And then I can actually factor out, let's take a look here, L naught times 1 plus alpha t. Okay, so think about what's going on here. If I want the final length of my object, if it's a long thin tube, I can take the original length, multiply it by 1 plus some factor, and if this is positive, it will stretch, my final length will be bigger than my original length. If this happens to be negative, I'm cooling it down, this factor will be less than 1, and it will shrink from its original length to some smaller value. I'm not saying you have to derive this, but just realize we can get to other pieces of information if we think about how this works out. So it might be useful, maybe, I'm not saying it will be, to have both of these on your cards or sheets or whatever. Same idea with area and volume. You guys know if you put $100 in the bank,